In 1961, a mathematician named Edward Lorenz was running a weather simulation on a primitive computer when he decided to save time by rounding a single number from 0.506127 to 0.506. When he returned, the weather pattern on his screen had transformed into something utterly different, as if he had simulated an entirely different planet. This is the story of how a shortcut in a weather equation accidentally revealed one of the most profound truths about reality itself, that the universe is far stranger, more interconnected, and more unpredictable than anyone had imagined. We will trace chaos theory from its accidental birth through its philosophical implications, exploring how it changed our understanding of determinism, predictability, and what it means for the future to be genuinely unknowable. From Edward Lorenz's weather equations to the fractals of Benoit Mandelbrot, from the three-body problem that troubled Newton to the strange attractors that haunt phase space, we will discover how chaos is not disorder but a different kind of order entirely, one that challenges everything philosophy thought it knew about cause and effect. The butterfly effect is often misunderstood as mere metaphor, a poetic way of saying everything is connected, but it emerged from rigorous mathematical discovery, from equations scribbled on blackboards at MIT and weather models churning through vacuum tube computers. Edward Norton Lorenz, born May 23, 1917 in West Hartford, Connecticut, was not looking for philosophical revolution when he set up his weather simulation that winter day. He was a meteorologist trying to solve a practical problem. Why are weather forecasts so unreliable? He had spent years studying atmospheric dynamics, had served as a weather forecaster for the Army Air Corps during World War II, and had become fascinated by the question of whether the atmosphere's behavior could be captured in mathematical equations. His computer, a Royal McBee LGP-30, was primitive by any measure. It filled a desk, hummed with the heat of its components, and could perform about 60 operations per second, a pace that would seem glacial within a decade. Lorenz had programmed it with 12 equations representing a simplified model of atmospheric convection, rising and falling air currents, temperature gradients, the basic mechanics of weather. The computer would calculate each step forward in time, printing out numbers that represented wind speed, temperature, and other variables. Over hours, these numbers would trace out the evolution of his miniature atmosphere. On this particular day, Lorenz wanted to examine one sequence more closely. Rather than start the simulation from the beginning, he decided to restart it from the middle, typing in the numbers the computer had printed out earlier, but the computer stored numbers to 6 decimal places in its memory while only printing 3. The number 0.506127 became 0.506, a difference of about 1 part in 1,000. Trivial, negligible. The kind of rounding error that happens constantly in any practical calculation. He left the computer running and went down the hall for coffee. When he returned an hour later, expecting to see the same weather pattern he had seen that morning, he found something impossible. The new simulation had diverged completely from the original. Where the first run had shown a particular pattern of highs and lows, the second showed something entirely different, not slightly different. Not a little bit off, completely, utterly transformed. His first assumption was that the machine had malfunctioned. Vacuum tubes failed, circuits overheated, but the computer was running normally, and when he checked his work, the equations were correct. He ran the simulation again. Same result. The tiny difference in initial conditions had grown, exponentially, until it dominated everything. 2 weather systems that started almost identically had become as different as summer and winter. Most scientists would have treated this as a nuisance, an unfortunate demonstration that weather modeling needed more precision. Lorenz recognized it as something far more significant. He had stumbled onto what would later be called sensitive dependence on initial conditions, and it would not just change meteorology, it would transform how we understand causation itself, how we think about the relationship between knowledge and prediction, how we conceive of the future's relationship to the past. But Lorenz's discovery had been anticipated, in a way 7 decades earlier, by a French mathematician working on a completely different problem. Henri Poincaré, studying the gravitational dance of celestial bodies, had encountered the same troubling phenomenon. and had tried to warn the scientific world about it. His warning had been ignored, buried in journals too mathematical for most physicists to parse, too abstract to seem relevant to practical science. It would take computers and Lorenz's accident for the message to finally break through. What Lorenz had found, and what Poincaré had glimpsed, was that the universe operates according to rules far more subtle than the clockwork mechanisms that science had celebrated since Newton. For 2 centuries, physics had promised that the cosmos was, in principle, completely predictable. Pierre-Simon Laplace had articulated this vision most clearly in 1814. Give him the position and velocity of every particle in the universe, and he could calculate the entire future and reconstruct the entire past. The universe was deterministic. Cause led to effect in an unbreakable chain. Mystery was merely ignorance waiting to be dispelled by better measurement and more powerful calculation. Chaos theory shattered this dream not by showing that the universe was random, but by revealing something stranger, that deterministic laws could produce behavior that was for all practical purposes unpredictable. The future was not open or indeterminate in the way quantum mechanics suggested. The equations were completely deterministic. There was no dice-throwing God, no fundamental randomness, and yet the future was still unknowable, sealed off from prediction by the exponential amplification of tiny uncertainties. This revelation has profound implications that ripple through philosophy, touching questions about free will, knowledge, causation, and what it means to understand something. If the universe is deterministic but unpredictable, where does that leave human agency? If tiny causes can have enormous effects, how do we think about responsibility, about control, about the relationship between intention and outcome? If simple equations can produce infinite complexity, what does that mean for reductionism, for the hope that knowing the parts will reveal the whole? The story of chaos theory is a story about the limits of human knowledge, but it is not a story of defeat. What Lorenz and those who followed him discovered was not that nature is incomprehensible, but that it is more subtle, more rich, more genuinely surprising than the mechanical philosophy had allowed. Chaos reveals a universe that is ordered but not rigid, patterned but not predictable, deterministic but not predetermined in any meaningful sense. It is a vision of reality that makes room for both law and novelty, for both structure and genuine openness. To understand how we arrived at this new vision, we need to go back to the world Lorenz inherited, the confident universe of clockwork stars and calculable futures, the Enlightenment dream of perfect knowledge that dominated science for 200 years before a tiny rounding error revealed its fatal flaw. In the year 1814, a French mathematician named Pierre-Simon Laplace published an essay that contained one of the most audacious claims ever made about the nature of reality. Laplace imagined an intelligence vast enough to know the position and velocity of every particle in the universe at a single moment. Given this perfect knowledge of the present, he argued, such an intelligence could calculate everything that would ever happen and everything that had ever happened. The future would be as certain and knowable as the past. Nothing would be hidden, nothing would be surprising, nothing would be genuinely new. He called this hypothetical intelligence a demon, though the word was meant less as theology and more as thought experiment, a way of pushing an idea to its logical extreme. The claim was not mere speculation. Laplace was one of the most brilliant mathematical minds of his age, a man who had transformed astronomy and probability theory, who had demonstrated how Newton's laws could account for the intricate dances of planets and moons without divine intervention. When he presented Napoleon with his monumental work on celestial mechanics, the emperor reportedly asked where God fit into his system. Laplace replied that he had no need of that hypothesis. His demon was the ultimate expression of this confidence, a universe that ran like clockwork, perfectly deterministic, its every motion dictated by mathematical law. If you knew enough, you could know everything. This vision did not emerge from nowhere. It was the culmination of a revolution that had begun a century and a half earlier, when Isaac Newton had published his Principia Mathematica in 1687. Newton had done something extraordinary. He had taken the messy, complicated motions of heavenly bodies and terrestrial objects and shown that they all obeyed the same simple laws. An apple falling from a tree and the moon orbiting Earth were not different kinds of phenomena. They were the same phenomenon, gravity, following identical mathematical rules. The force between two objects could be calculated precisely, and from that calculation, you could predict where anything would be at any moment in the future, or discover where it had been at any moment in the past. The implications went far beyond astronomy. Newton's laws suggested that the entire physical universe was a vast mechanism, each part pushing and pulling on every other part according to fixed rules. If you could specify the initial conditions, the starting positions and velocities of all the pieces, then the mathematics would tell you everything that followed, cause produced effect with absolute reliability. The universe was not capricious or mysterious. It was lawful, orderly, comprehensible through reason and calculation. This mechanical philosophy transformed not just science but culture. The Enlightenment of the 18th century was animated by the belief that human reason could penetrate any mystery, solve any problem, understand any phenomenon. What Newton had done for the heavens, surely others could do for chemistry, for biology, for the workings of the human mind itself. Libraries filled with encyclopedias attempting to catalogue all knowledge. Philosophers spoke of natural law governing human societies with the same certainty that gravity governed planets. There was an intoxicating optimism in the air, a sense that humanity was finally emerging from centuries of ignorance and superstition into the clear light of rational understanding. Laplace's demon was the perfected symbol of this worldview. It represented not just what was known, but what was in principle knowable. The universe kept no secrets that mathematics could not eventually reveal. Every event, no matter how complex, was the inevitable consequence of what had come before, linked by an unbroken chain of cause and effect, stretching back to the initial conditions of the cosmos itself. Prediction was not merely possible, but guaranteed, limited only by the practical difficulty of gathering information and performing calculations. With better instruments and more powerful mathematics, the fog would lift, the future would become transparent. But this crystal-clear vision brought with it a troubling shadow. If everything that happens is the necessary consequence of what came before, if the present state of the universe determines all future states with absolute certainty, then what becomes of human choice? What becomes of free will? The question had haunted philosophers for centuries, but mechanical determinism gave it new urgency and new precision. Your decision to read these words, to think these thoughts, to act tomorrow in whatever way you will act, would all be the inevitable result of particles following laws. You would not be choosing freely. You would be a clockwork automaton, perhaps more complicated than the mechanical dolls that entertained European courts, but no more genuinely free. Some philosophers embraced this conclusion. Baron de Holbach, writing in 1770, declared that free will was an illusion born of ignorance. We feel free only because we do not perceive the causes that determine our actions. Others tried to find room for freedom within determinism, arguing that we could be free as long as we acted according to our own desires, even if those desires themselves were determined. But these attempts satisfied few. The mechanical universe seemed to leave no space for genuine agency, for the sense that we are authors of our actions rather than merely stages where inevitable processes play out. The scientists themselves often avoided these philosophical entanglements. Their job was to predict eclipses, calculate trajectories, understand how forces and motions related. If determinism troubled theologians and philosophers, that was not really their concern. The equations worked. The predictions came true. The clockwork kept time. Yet even in the 19th century, even at the height of this mechanistic confidence, there were hints that something was not quite right. James Clerk Maxwell, who unified electricity and magnetism into a single elegant theory, wrote in 1873 about what he called the instability of the physical universe. He noted that there were points where an infinitesimal difference in initial conditions could lead to vastly different outcomes. A rock balanced on a summit might fall to one side or the other, depending on perturbations too small to measure. A railway switch might direct a train toward one city or another, based on the position of a mechanism altered by a fraction of an inch. Maxwell recognized that these situations posed a challenge for prediction. You could not measure initial conditions with infinite precision. There would always be some uncertainty, some tiny error, and in certain systems, those tiny errors mattered enormously. But Maxwell's observations remained a footnote, a curiosity rather than a revolution. The successes of mechanical physics were too overwhelming, the predictions too accurate, the vision of the clockwork universe too compelling. Scientists continued to discover new laws, new forces, new ways of applying mathematics to nature. By the dawn of the 20th century, some physicists believed their work was nearly complete. The major questions had been answered. All that remained was to refine the measurements, calculate to more decimal places, fill in minor details. This confidence persisted even as relativity and quantum mechanics overturned Newtonian physics in the early 20th century. These new theories were strange and counterintuitive, but they were still fundamentally deterministic in their own ways. Einstein's equations of general relativity specified how space-time curved in response to matter and energy, allowing precise predictions about the cosmos. Quantum mechanics introduced probability into the heart of physics, but even there the wave function evolved deterministically according to the Schrödinger equation. The universe might be weirder than Newton had imagined, but it still seemed to follow laws, still seemed to be, in principle, calculable and predictable. The dream of Laplace's demon adapted but did not die. Perhaps the demon needed to understand quantum mechanics or relativity, but the basic promise remained: know enough about the present, and you can know the future. The universe was complicated, yes, but not incomprehensible. Science marched forward, accumulating knowledge, building bigger telescopes and more powerful calculating machines, confident that every mystery would eventually yield to systematic investigation. But even as this confident worldview reached its zenith, a French mathematician was discovering something deeply unsettling in the movements of celestial bodies, something that would remain buried in obscure journals for decades before anyone understood what it meant. In 1885, King Oscar II of Sweden announced a mathematical competition in honor of his 60th birthday. The prize would go to whoever could solve one of the oldest and most frustrating problems in celestial mechanics, prove that the solar system is stable. Newton's laws had explained how planets move, but they had left unanswered the question of whether those movements would continue forever in their elegant dance, or whether some subtle accumulation of gravitational tugs might eventually send the whole system into chaos. The question had haunted astronomers for 2 centuries. King Oscar, who fancied himself a patron of science, offered his prize to anyone who could finally put the matter to rest. Henri Poincaré seemed like exactly the sort of mathematician who might succeed. Born in 1854 in Nancy, France, he had already established himself as one of the most brilliant and versatile mathematical minds of his generation. He moved between fields with astonishing ease, contributing fundamental work to topology, number theory, and mathematical physics. Where other mathematicians specialized, Poincaré synthesized. Where others calculated, he visualized. He possessed an almost uncanny ability to see the geometric shape underlying algebraic problems, to perceive patterns that remained invisible to more methodical minds. When he turned his attention to King Oscar's prize, the mathematical community watched with anticipation. The question the competition posed was technically about the stability of the solar system, but the heart of the problem was something simpler and more fundamental: the three-body problem. Newton had shown how to calculate the motion of 2 bodies orbiting each other under mutual gravitational attraction. The mathematics was elegant and exact: 2 planets, 2 stars, a planet and its moon. Given their positions and velocities at any moment, you could predict their positions at any future time with perfect accuracy. But add a third body to the system, and everything changed. 3 objects, each pulling gravitationally on the other 2, created a mathematical nightmare. The equations became impossible to solve exactly. Astronomers could approximate, could calculate close enough for practical purposes, but the perfect predictive power that Newton's laws promised seemed to slip away. Poincaré approached the problem with characteristic boldness. Rather than attempting to find exact solutions which had defeated everyone who tried, He asked whether the system would at least remain stable. Would the three bodies continue orbiting in some bounded region of space, or might one eventually fly off to infinity? Could the orbits, even if they could not be calculated exactly, at least be shown to remain orderly? He developed new mathematical tools to attack the question, inventing much of what would later be called topology along the way. By 1889, he had produced a long and technically dense memoir that appeared to prove what everyone hoped: the system was indeed stable, and the orbits would remain bounded and regular. The judges awarded Poincaré the prize. His memoir was prepared for publication in the journal Acta Mathematica. The mathematical world celebrated. King Oscar had his answer, and Poincaré had confirmed the essential orderliness of the heavens. But then, as the memoir was being typeset for publication, a Swedish mathematician named Edvard Fragmen noticed something troubling in one of Poincaré's arguments. He wrote to Poincaré asking for clarification on a technical point. Poincaré, reviewing his own work more carefully, realized with growing horror that Fragmen was right to be confused. There was a gap in the reasoning, and when Poincaré tried to fill it, he discovered something that shocked him profoundly. The orbits were not stable and regular. They were not even close. What Poincaré found, when he corrected his error, was something that seemed almost impossible. The trajectories of three gravitating bodies could become extraordinarily complex, so tangled and convoluted that no amount of calculation would ever capture their full behavior. A body might orbit peacefully for thousands of cycles, then suddenly veer close to another, get flung outward, return, and enter into an entirely different pattern. The motion was deterministic, governed completely by Newton's laws, with no randomness or uncertainty in the physics itself. Yet it was also unpredictable in a way that went beyond mere computational difficulty. Poincaré attempted to describe what he was seeing. The trajectories, he wrote, form a kind of infinitely complex trellis, a web of curves so intricate that trying to trace them precisely would be hopeless. Two orbits that begin almost identically, differing by only the tiniest amount in initial position or velocity, could diverge dramatically over time, ending up in completely different regions of space. The problem was not that the mathematics was too difficult, though it certainly was. The problem was deeper. The system contained a kind of fundamental unpredictability that no increase in mathematical sophistication would ever overcome. He published his corrected memoir in 1890, and it won him the prize nonetheless. But Poincaré understood that he had not solved the problem King Oscar posed. He had instead discovered that the problem might be insoluble, not because mathematicians were not clever enough, but because the universe itself did not work the way everyone assumed. This was profoundly disturbing. Since Newton, mathematical physics had promised perfect predictability. Give me the positions and velocities of all particles at one moment. Laplace had essentially said, and I will calculate the entire future and past of the cosmos. Poincaré had found a crack in that promise, a place where deterministic laws produced behavior that was, for all practical purposes, impossible to predict. Rather than abandoning mathematics in despair, Poincaré did something remarkable. He invented a new way of thinking about dynamical systems. If you could not calculate exact trajectories, perhaps you could still understand their qualitative behavior. Instead of asking where precisely a planet would be at some future time, you could ask what kinds of motion were possible, what the space of all possible orbits looked like, whether there were patterns or structures that persisted even when exact prediction was impossible. He developed the concept of phase space, an abstract mathematical arena where each point represents not a location in physical space, but a complete state of the system. All positions and all velocities together, orbits become curves in this phase space, and understanding the geometry of these curves could reveal things that calculation never would. This was the birth of qualitative dynamics, of topology applied to physics, of a whole new way of thinking about motion and change. But almost nobody understood what Poincaré had found. The mathematics was too abstract, too divorced from the concrete questions that physicists and astronomers wanted answered. His corrected memoir was published in a journal that few scientists read carefully. The work was admired for its technical brilliance, but its deeper implications remained obscure. Poincaré himself seemed unsure what to make of his discovery. He had opened a door onto something strange and unsettling, a place where Newton's clockwork universe showed signs of fundamental unpredictability, but he could not see clearly what lay beyond that door. For the next 70 years, Poincaré's insight remained buried in the literature of advanced mathematics. A few specialists knew of it, but it seemed like a curious exception, a pathological case of interest only to pure mathematicians concerned with rigor and abstraction. The physicists and astronomers went on assuming that the solar system was, for all practical purposes, predictable. They developed increasingly sophisticated perturbation methods to approximate planetary motions. They assumed that the complications Poincaré had found were mathematical artifacts that would vanish when you looked at real physical systems. The idea that simple deterministic laws could produce genuinely unpredictable behavior seemed too strange to take seriously, too much at odds with the mechanical worldview that had served science so well. Poincaré died in 1912, long before anyone would fully appreciate what he had discovered. The three-body problem remained unsolved, not because the right mathematician had not yet appeared, but because Poincaré had shown it was unsolvable in the traditional sense. The cosmos he had glimpsed was not the perfect clockwork that Laplace imagined. It was something wilder, more subtle, more genuinely surprising. But that revelation would have to wait for a different era, for computers and weather simulations, and a mathematician who would stumble onto the same strange truth from an entirely different direction. Poincaré's insight vanished into the mathematical literature, too abstract and too disturbing for most scientists to grapple with. It would take the arrival of the computer age and one mathematician's desire to take a shortcut for chaos to be rediscovered. Edward Lorenz came to meteorology by accident, which seems fitting for a man who would discover that accidents govern far more than anyone suspected. Born in West Hartford, Connecticut in 1917, he entered Dartmouth College intending to study mathematics, drawn to its clean certainties and elegant proofs. But the Second World War intervened, as it did for so many young men of his generation, and the military needed weather forecasters more urgently than it needed pure mathematicians. Lorenz found himself trained in meteorology, learning to read the chaos of atmospheric data and translate it into predictions that might save lives or doom missions. The work fascinated him in ways pure mathematics never had. Weather was mathematics applied to something gloriously, maddeningly real. After the war, Lorenz could have returned to pure mathematics, but something about the weather had caught him. He pursued graduate studies at MIT, earning a doctorate in meteorology while keeping one foot firmly planted in mathematical theory. By the late 1950s, he had become a professor at MIT, respected but not particularly famous, working on problems that most mathematicians considered too messy and most meteorologists considered too abstract. He was interested in a question that seemed both practical and profound. Could you create a mathematical model of weather that would let you predict it? The idea was not new. Meteorologists had been trying to forecast weather systematically since the 19th century, but their tools were hopelessly limited. They could observe, they could see patterns, they could make educated guesses based on experience. What they could not do was calculate. The equations governing atmospheric behavior, derived from fundamental physics, were far too complex for any human to solve by hand. A complete weather calculation for even a small region would require millions of arithmetic operations, more than a team of mathematicians could complete in a lifetime, by which time the weather would have long since moved on. But by 1960, something new had entered the world: the electronic computer. These machines were still primitive by any modern measure, massive and temperamental, with less computing power than a contemporary pocket calculator. Yet to scientists like Lorenz, they represented a revolution. For the first time in history, you could actually solve the equations. You could take the fundamental laws of physics, express them in mathematical form, and calculate what should happen next. Lorenz acquired a Royal McBee LGP30, one of the first desk-sized computers. Desk-sized meant roughly the size of a large refrigerator, humming and clicking as vacuum tubes performed their calculations, printing results on endless rolls of paper that curled onto the floor. By the standards of 1961, it was a marvel. It could perform 60 operations per second. It had just over 4,000 bytes of memory. Lorenz treated it with a mixture of reverence and frustration that early computer users knew well. It broke down regularly. It required constant maintenance. But when it worked, it could calculate. He built a simplified model of weather, stripping away most of the atmosphere's complexity to focus on a few essential features. 12 equations, 12 variables, not realistic enough to actually forecast tomorrow's rain, but realistic enough, he hoped to capture something true about how weather behaved. He would set initial conditions, representing the state of his imaginary atmosphere at a starting moment, then let the computer calculate forward in time, showing him how this miniature weather would evolve. The results were encouraging. His model produced weather-like behavior, patterns that rose and fell, shifted and changed, never quite repeating but never spiraling into nonsense. He ran simulations, adjusted parameters, tried to understand what his equations were telling him. On one particular day in the winter of 1961, he decided to examine a sequence more carefully. He had run a simulation earlier and wanted to see more detail in the middle portion. Rather than restart from the beginning, he took a shortcut. He would restart from the middle, typing in the numbers the computer had printed out earlier, and let it calculate forward from there. He typed in the starting values, careful but not obsessive about precision. The computer had calculated and printed results to 6 decimal places, but he only typed 3.506 instead of 0.506127. The difference seemed trivial, less than 1 part in 1,000. In any practical sense, these were the same numbers. He started the simulation, then walked down the hall to get coffee while the machine clattered through its calculations. When he returned an hour later, expecting to see his earlier results reproduced, he found something impossible. The weather on the new printout was completely different, not slightly different, not a minor variation, but utterly fundamentally transformed. Where the first run had shown a particular pressure pattern, the second showed the opposite. Where the first had developed a specific circulation, the second went somewhere else entirely. It was as if he had simulated weather on 2 different planets, yet he had changed almost nothing. The equations were identical. The starting conditions were, for all practical purposes, the same. How could such a tiny difference produce such massive divergence? His first assumption was that the computer had malfunctioned. These machines were notoriously unreliable. A vacuum tube could fail, a connection could loosen, and the calculations would go wildly wrong. He checked the equipment. Everything appeared fine. He ran the simulation again more carefully. The results repeated. It was not a malfunction. He ran other simulations, deliberately introducing tiny changes to initial conditions. Every time, the same pattern emerged. After a few cycles through his model's timeline, tiny differences exploded into total transformation. Lorenz began investigating systematically, with the methodical care that marks genuine science. He varied the size of the initial differences, tracking how quickly they grew. He tried different starting conditions, checking whether some states were more stable than others. He modified his equations, testing whether this behavior appeared in simpler or more complex systems. The answer became increasingly clear and increasingly disturbing. This was not a bug. This was not a peculiarity of his particular model. This was something fundamental about the mathematics itself. What he had discovered was that his deterministic equations with no randomness or uncertainty built in, equations that in principle allowed you to calculate the future with perfect precision, were nevertheless unpredictable in practice. The reason was exponential amplification of tiny uncertainties. Take 2 starting conditions that differ by 1 part in 1,000. Let the system evolve. After one step, they might differ by 2 parts in 1,000. After another step, 4 parts in 1,000. The difference doubles with each iteration, growing exponentially until the 2 versions of reality have nothing in common. This meant that perfect prediction required perfect knowledge of initial conditions. Not good knowledge, not excellent knowledge, but absolutely perfect knowledge, infinite precision in every measurement. Since such perfection was impossible, even in principle, long-term prediction became hopeless. You could know all the laws, understand all the equations, have unlimited computing power, and still you could not predict what would happen. The future was sealed behind a barrier of exponentially growing uncertainty. The philosophical implications crystallized slowly as Lorenz worked through the mathematics. He was looking at something that should not exist according to the worldview he had inherited. Determinism was supposed to imply predictability. If the laws of nature determine everything, if every effect has a cause, if nothing happens by chance, then perfect knowledge of the present should yield perfect knowledge of the future. That was the promise of classical physics, the foundation of the clockwork universe. Lorenz had found a clockwork that could not be read, a mechanism that was perfectly deterministic and perfectly unpredictable at the same time. He published his findings in 1963 in the Journal of the Atmospheric Sciences in a paper titled Deterministic Non-Periodic Flow. The title was deliberately dry, technical, understated. The content was revolutionary. He had created graphs showing the behavior of his simplified weather system in what mathematicians call phase space, a realm where each point represents a complete state of the system. The trajectory traced by his weather model formed a strange shape, a double spiral that looped endlessly, without ever repeating, never settling into any pattern, never crossing itself, confined to a particular region of phase space, yet exploring it with infinite variation. It looked like a butterfly's wings, though that comparison would come later. Most atmospheric scientists ignored the paper. It was too mathematical, too abstract, too removed from the practical work of forecasting tomorrow's weather. Mathematicians who might have appreciated its depth rarely read meteorology journals. The paper sat in the literature like an unexploded bomb, waiting for someone to recognize what it contained. But a few people understood immediately. They recognized that Lorenz had not merely discovered something about weather, he had discovered something about the nature of mathematical law itself. Lorenz had stumbled onto something that seemed impossible, equations that were completely deterministic, with no randomness whatsoever, yet produced behavior that was for all practical purposes unpredictable. But what exactly had he found? Lorenz had found something, but what exactly? When he returned to his desk that day to find two diverging weather patterns, he faced a puzzle that seemed to violate basic logic. The equations governing his simulation contained no randomness whatsoever. Every calculation followed inexorably from the one before, yet somehow, changing a number in the 6th decimal place had transformed the entire trajectory of his simulated atmosphere. The computer had not malfunctioned. The mathematics had not broken down. Something far stranger was happening. He called it sensitive dependence on initial conditions, a phrase deliberately chosen for its precision. The sensitivity was not vague or metaphorical. It could be measured, quantified, expressed in the rigorous language of mathematics. What Lorenz had discovered was that in certain systems, infinitesimally small differences in starting conditions grow exponentially over time, not linearly, where a tiny change produces a proportionally tiny effect, exponentially, where differences double, then double again, expanding at an accelerating rate until prediction becomes meaningless. Consider what exponential growth actually means. If you fold a piece of paper in half, then fold it again, then again, the thickness grows deceptively fast. After 7 folds, you have a stack about as thick as a notebook. After 20 folds, if such a thing were physically possible, you would have a tower reaching from the ground to low Earth orbit. After 42 folds, the stack would reach the moon. This is not complexity or randomness. It is the inexorable logic of doubling, the mathematics of expansion that respects no intuition about proportionality. In Lorenz's weather equations, measurement errors behaved like this. Suppose you could measure the temperature at a point in the atmosphere to within 1/10 of a degree. That uncertainty, tiny as it is, would double in the simulation every few time steps. Within days of simulated weather, your prediction would contain errors larger than the phenomena you were trying to predict. The forecast would become useless not because the equations were wrong or the computer was insufficient, but because the system itself amplified uncertainty at an exponential rate. This was not mere complexity, though the distinction took years for the scientific community to grasp. Complex systems can be difficult to analyze, challenging to compute, hard to understand, but complexity alone does not produce sensitive dependence. A complicated machine with 10,000 gears might be difficult to predict simply because tracking all those moving parts exceeds our computational resources. Give us a big enough computer, enough time, enough precision in our measurements, and we could predict it perfectly. Chaos is different. In a chaotic system, no amount of computational power helps, because the act of measurement itself can never be perfect enough. The universe does not provide infinite precision. Quantum mechanics sets a lower bound on how accurately we can measure position and momentum simultaneously. Practical limitations impose even cruder bounds, and in a system with sensitive dependence, whatever error remains in your measurement, however small, will eventually render your prediction worthless. Nor was this randomness, though here too the confusion persists. Random systems are unpredictable because they contain genuine chance, dice rolls written into their fundamental laws. Quantum mechanics has this character. The decay of a radioactive atom happens at a genuinely random moment, with no hidden variables determining when, but Lorenz's equations contain no dice rolls, no random number generators, no chance whatsoever. Given the exact same starting conditions, they would produce the exact same weather pattern every single time. The unpredictability arose not from randomness, but from impossibility of knowing the starting conditions exactly enough. The future was fixed, determined, inevitable. It was also unknowable. To visualize what his equations were doing, Lorenz invented a way of looking at systems that has since become one of the most powerful tools in modern science. He created what mathematicians call phase space, an abstract landscape where each point represents not a location in physical space but a complete state of the system. For weather, a point in phase space might encode the temperature, pressure, humidity, and wind speed at every location in the atmosphere at a single moment. As the weather evolves, this point traces a path through phase space, moving according to the mathematical rules Lorenz had written down. What he discovered, when he plotted these paths, was an object of haunting beauty and profound strangeness. The trajectories did not wander randomly through phase space. They did not settle into simple repeating patterns. Instead, they traced out a shape that came to be called the Lorenz attractor, a double spiral resembling the wings of a butterfly or the eyes of an owl. Paths would circle one lobe of the spiral, then suddenly switch to the other lobe, then back again, never quite repeating, never escaping the overall shape. This was a new kind of mathematical object. It was neither a point, nor a line, nor a surface. It existed in a fractional dimension, a concept that would be developed more fully later by Benoit Mandelbrot. If you zoomed into any portion of the attractor, you found the same intricate structure, repeated at smaller scales, infinite detail, packed into a finite region. It was a fixed entity, unchanging in its overall form, yet every trajectory through it was unique, never retracing its exact path. The attractor represented all possible weathers that Lorenz's equations could produce, an infinite collection of destinies contained in a single stable structure. The sensitive dependence manifested in how trajectories behaved on this attractor. Two paths that started arbitrarily close together would initially stay near each other, following almost the same route around the spiral, but then they would diverge, pulled apart by the exponential expansion of differences, until they bore no resemblance to each other at all. They remained on the same attractor, confined to the same overall shape, but their specific locations became completely uncorrelated. This was the key insight. The system had definite structure, ironclad rules, yet produced effective unpredictability. For philosophy, the implications were staggering. For more than a century, determinism and predictability had been treated as nearly synonymous. If the universe ran according to fixed laws, if cause inevitably produced effect, then in principle, given enough information and computational power, the future could be calculated. Laplace's demon needed only perfect knowledge of the present to deduce all of history, forward and backward. Chaos theory revealed that this was false. A system could be completely deterministic, with every event caused by prior events according to knowable laws, and yet remain unpredictable even in principle. The gap between determinism and predictability was not a gap in human knowledge or technological capability. It was not a temporary limitation that better instruments or faster computers would eventually overcome. It was woven into the structure of certain systems themselves. The equations determined the future completely, but they did so in a way that made the future inaccessible to anyone who could not measure the present with infinite precision. Since such measurement is impossible, the future in chaotic systems is not merely unknown but unknowable. This changed what determinism meant. The classical picture was of a universe running like an immense clockwork, each gear turning with inevitable precision, the entire mechanism predictable to anyone who understood its construction. Chaos revealed a universe that was deterministic in its laws, but possessed of genuine novelty in its outcomes. The laws did not change. The causation remained ironclad. Yet the unfolding of events could surprise even an observer who knew all the laws and had measured the present state as carefully as physics allowed. Knowledge itself had limits that were not merely practical but fundamental. You could understand the rules completely and still not know what would happen next. You could have the equations in hand, the most powerful computers imaginable, measurements of extraordinary precision, and still, given enough time, your predictions would fail catastrophically. The future would veer off in directions you had not foreseen, not because the rules had changed, not because chance intervened, but because tiny uncertainties amplified beyond recovery. Lorenz had uncovered something philosophers had not quite imagined: a deterministic universe that nevertheless contained irreducible mystery, a cosmos of law that produced genuine surprise, a reality where cause and effect operated with perfect fidelity, yet offered no pathway to perfect foreknowledge. The implications would ripple through science and philosophy for decades, reshaping questions about free will, causation, and the nature of scientific explanation itself. Understanding sensitive dependence was one thing, but Lorenz needed to communicate this bizarre discovery to a skeptical scientific community. When he finally did, he chose a metaphor that would become perhaps too famous for its own good. By 1972, Edward Lorenz had spent more than a decade trying to explain what he had discovered in that weather simulation. He had published his findings in the Journal of the Atmospheric Sciences back in 1963, in a paper titled Deterministic Non-Periodic Flow that was mathematically rigorous and deeply important, and almost entirely ignored outside the small community of theoretical meteorologists. The title was accurate but not exactly designed to capture the imagination. The paper contained everything: the strange attractor, the sensitive dependence on initial conditions, the profound implications for prediction, but hardly anyone noticed. This was not unusual in science. Profound discoveries often arrive in technical language, buried in specialized journals, their revolutionary nature visible only to those who already speak the dialect. Lorenz's work was particularly difficult to communicate, because it violated intuition so thoroughly. People could accept that complex systems were unpredictable. What they struggled to grasp was that simple systems could be unpredictable too, that three differential equations with no randomness whatsoever could produce behavior that was, for all practical purposes, impossible to forecast beyond a certain horizon. In late December of 1972, Lorenz was invited to give a talk at the annual meeting of the American Association for the Advancement of Science in Washington. The conference was massive, sprawling across multiple hotels, with hundreds of presentations competing for attention. Lorenz's talk was scheduled in a session on predictability in atmospheric flows. He needed a title. This is where Philip Merriles enters the story. Merriles was a meteorologist helping to organize the session, and when Lorenz had not provided a title by the deadline, Merriles took the liberty of creating one himself. The title he chose was a question: predictability. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? Lorenz had never mentioned butterflies. In his original paper, when he needed an example of a small perturbation, he had used the flap of a seagull's wings, but seagulls lacked poetry. Merriles understood something about metaphor that perhaps Lorenz, focused on mathematical precision, had not fully appreciated. Science needs images that stick in the mind, needs language that carries ideas beyond the seminar room into wider consciousness. The butterfly was perfect. It was delicate, beautiful, associated with transformation and fragility. It was also absurd in exactly the right way. The notion that something as gentle as a butterfly's wing could eventually influence something as violent as a tornado captured the mathematical truth, while simultaneously inviting disbelief. The title made people want to hear the answer. What Lorenz actually said in that talk was careful and precise. He was not claiming that a specific butterfly caused a specific tornado. He was not suggesting that if you could somehow prevent that butterfly from flapping, you would prevent that tornado. The relationship was far more subtle and far stranger than simple cause and effect. What he meant was this: in a chaotic system like the atmosphere, tiny differences in initial conditions grow exponentially over time. If you ran two weather simulations that differed only by something as small as whether a butterfly had flapped its wings in one version but not the other, those two simulations would initially produce nearly identical forecasts, but the tiny difference would begin to grow. Within days, the forecasts would diverge noticeably. Within weeks, they would show completely different weather patterns. Within months, one simulation might have a tornado in Texas while the other had clear skies. The butterfly was not causing the tornado. The butterfly was a stand-in for the unavoidable uncertainty in any measurement of the atmosphere's current state. You can never know the exact positions and velocities of all the air molecules, the precise temperature at every point, the exact moisture content everywhere. Your measurements always have some tiny error, some finite precision. In a linear system, those tiny errors stay tiny. In a chaotic system, they grow until they completely dominate the forecast. This is not magic. This is not mysticism. This is mathematics. But the metaphor of the butterfly made it sound almost mystical, and that was both its power and its danger. The talk resonated in ways Lorenz could not have predicted. The butterfly effect entered popular culture. It appeared in movies and novels in casual conversation. People used it to suggest that everything was connected to everything else in mysterious ways, that small actions could have enormous consequences across vast distances, that reality was fundamentally inexplicable and governed by forces beyond human comprehension. Some of this was true, in a sense. Small actions can have large consequences. Reality is more interconnected than naive intuition suggests. But the way the metaphor was used often missed or distorted what Lorenz had actually discovered. The butterfly effect became a kind of secular magic, invoked to explain coincidences or to suggest that individual choices ripple out in unpredictable ways to reshape the world. What was lost in the popularization was the specificity of the phenomenon. Sensitive dependence on initial conditions occurs in chaotic systems, which have particular mathematical properties. Not every system is chaotic. Not every small change grows exponentially. The butterfly effect is not a general principle that applies everywhere to everything. It is a specific behavior that emerges from specific kinds of nonlinear dynamics. Moreover, chaos is still deterministic. If you could somehow know the exact state of the atmosphere down to the position of every molecule, and if you had infinite computational power to solve the equations, the future weather would unfold in a completely determined way. The butterfly has not introduced randomness or free will into the weather. It has simply revealed that perfect knowledge is impossible, and that even in a deterministic universe, prediction has hard limits. The danger of metaphor in science is that it simplifies in order to communicate, and sometimes the simplification erases the very thing that makes the discovery profound. The butterfly is vivid and memorable, but it can make chaos theory seem like it is about coincidence and cosmic connection, rather than about the mathematical structure of certain differential equations. It can make sensitive dependence sound poetic rather than technical. Yet metaphors are necessary. Science cannot exist only in equations. Ideas must travel from specialists to non-specialists, must become part of how we collectively understand reality. The butterfly did that. It gave chaos theory a public face. It helped people grasp that the universe is not as clockwork predictable as Laplace had imagined. It communicated, however imperfectly, that there are limits to knowledge that have nothing to do with human ignorance and everything to do with the nature of certain kinds of systems. Lorenz himself seemed ambivalent about the metaphor's fame. He continued to give careful technical talks to scientific audiences. He wrote papers with titles like Atmospheric Predictability, as revealed by naturally occurring analogues that were precise and thorough and not designed for mass appeal. But he also recognized that the butterfly had accomplished something his equations alone could not. It had made people curious. It had opened a door. The question he posed in that title was deliberately provocative, and the answer he gave was nuanced. Yes, in a chaotic system, something as small as a butterfly's wing can eventually influence whether a tornado forms. No, this does not mean butterflies control the weather, or that we should treat them as causally responsible for storms. What it means is that the atmosphere is sensitive to initial conditions in a way that makes long-range prediction fundamentally impossible, regardless of how much data we gather or how powerful our computers become. This was the message that needed to spread. Not that the universe is magical, but that it is more subtle than we thought. Not that cause and effect have broken down, but that they operate in ways that make the future genuinely unknowable, even when it is completely determined. The butterfly was a messenger, carrying these ideas out of meteorology journals and into wider consciousness. Like all messengers, it sometimes garbled the message, but it delivered it nonetheless. While Lorenz was carefully explaining sensitive dependence to meteorologists, other scientists across different fields were independently discovering that chaos lurked in their equations too. The revelation was spreading. Edward Lorenz had discovered sensitive dependence in weather equations, but throughout the early 1970s, he remained largely unaware that scientists across wildly different disciplines were encountering the same mathematical strangeness in their own work. A theoretical ecologist studying insect populations, a physicist examining fluid turbulence, a mathematician investigating abstract iteration, each believed they had stumbled upon an isolated oddity in their particular corner of science. The profound realization that would soon dawn was this chaos was not an anomaly. It was everywhere. Robert May arrived at the discovery almost by accident, which seems fitting for a phenomenon defined by unexpected outcomes. Born in Australia in 1936, May had trained as a theoretical physicist before shifting his attention to biology in the late 1960s. He brought to ecology something that field had previously lacked: a physicist's comfort with mathematical abstraction and a willingness to follow equations wherever they led, even into uncomfortable territory. In 1974, while working at Princeton, May was examining one of the simplest models in population biology, an equation so elementary it was taught to undergraduates. The logistic map, as it was called, described how a population of insects or fish might grow from one generation to the next, accounting for both reproduction and the limiting effects of crowding or food scarcity. The mathematics involved nothing more sophisticated than multiplication and subtraction. May expected orderly, predictable behavior. What he found instead was madness. When he ran the equation with certain parameter values, populations would settle into stable equilibrium, just as expected. But as he adjusted a single variable, the growth rate, the behavior transformed. The population began to oscillate between two values, then 4, then 8. Further adjustment produced oscillations of 16, 32, 64. Then abruptly, the pattern shattered completely. The population fluctuated wildly from generation to generation with no discernible pattern whatsoever. Pure chaos emerging from an equation a child could understand. May checked his calculations obsessively, certain he had made an error. He had not. The equation was deterministic, containing no random elements, yet it produced population fluctuations that appeared utterly random. He was seeing in biology what Lorenz had seen in meteorology, though neither man knew of the other's work yet. May published his findings in 1976 in the journal Nature, in a paper that would become one of the most cited in theoretical biology. His message carried an unsettling implication for his field. Even if ecologists knew every relevant factor affecting a population, even if their models were perfectly accurate, they might still be unable to predict future population sizes. The insects themselves were not behaving randomly. They were following deterministic rules, but those rules produced unpredictability as surely as if dice were being rolled. May had demonstrated that you did not need complex ecosystems with thousands of interacting species to get unpredictable dynamics. A single species, governed by a single equation, was sufficient. Chaos, it seemed, required neither complexity nor randomness. It emerged from simplicity itself. While May was discovering chaos in populations, Mitchell Feigenbaum was finding something even more peculiar. Chaos had universal properties. Feigenbaum, working at Los Alamos National Laboratory in 1975, had become obsessed with period doubling, the same cascade that May had observed where stable behavior splits into oscillations of 2, then 4, then 8. Using a pocket calculator and extraordinary persistence, Feigenbaum calculated the ratio between successive bifurcations, the rate at which the doubling accelerated. He discovered that this ratio converged to a specific number 4.669216. He checked other equations, completely different mathematical functions. The same number appeared. He tried systems from physics, from chemistry, from electronics, always the same number. Feigenbaum had discovered a universal constant of chaos, akin to P or the golden ratio but governing the transition from order to disorder. No matter what system you examined, no matter what the underlying mechanisms, if it exhibited period doubling on the route to chaos, it followed the same mathematical rhythm. Chaos, it turned out, was not lawless. It had its own deep structure, its own hidden regularities. Feigenbaum published his results in 1978, and at first almost no one believed him. The claim seemed too strange that systems as different as dripping faucets and electrical circuits and chemical reactions would share identical mathematical properties as they descended into chaos. But experimental verification came quickly. Physicists tested Feigenbaum's predictions in fluid dynamics experiments, watching water flow become turbulent. Chemists observed oscillating reactions in stirred beakers. Electronic engineers studied nonlinear circuits. Every test confirmed the same universal ratios. Chaos was not a collection of isolated oddities. It was a unified phenomenon with its own mathematics, its own constants, its own laws. The discoveries multiplied with startling speed through the mid and late 1970s. Scientists began recognizing chaotic behavior in systems they had studied for decades without understanding what they were seeing. Turbulent fluid flow, which had frustrated physicists since the 19th century, revealed itself as a chaotic process. The erratic dripping of a leaky faucet followed the same mathematical patterns as May's insect populations. Chemical reactions that oscillated in maddeningly irregular patterns were chaotic dynamical systems. Electrical circuits built from simple components could generate chaos. Heart arrhythmias, epileptic seizures, stock market fluctuations, all displayed the signatures of deterministic chaos. Everywhere scientists had attributed irregularity to randomness or to hopelessly complex interactions, chaos theory offered a different explanation: sensitive dependence on initial conditions in nonlinear dynamical systems. The realization spread that classical physics had gotten something fundamentally wrong. The implicit assumption underlying centuries of science was that simple systems behave simply and complex behavior requires complex causes. Chaos theory inverted this understanding. Simple deterministic rules could produce behavior of arbitrary complexity. A system with just 3 variables, like Lorenz's weather equations, could generate infinitely varied patterns. Predictability and determinism, which had been assumed to be synonymous since Laplace, were actually separate properties. The universe could be fully deterministic, governed by precise mathematical laws, and still be fundamentally unpredictable beyond short time horizons. This was not a minor technical correction. It represented a philosophical earthquake. By the late 1970s, scientists working on chaos were beginning to find each other. Conferences brought together meteorologists, ecologists, physicists, mathematicians, chemists, each describing the same mathematical structures in radically different contexts. A community was forming, united by the recognition that they were all studying facets of the same phenomenon. The Santa Fe Institute, founded in 1984, would become the intellectual home for this new science of complexity and chaos. But even before formal institutions arose, an informal network of researchers was sharing preprints, visiting each other's laboratories, recognizing kindred spirits working on the same deep problems from different angles. The excitement was palpable. They had discovered something genuinely new about how nature works, something that had been hiding in plain sight for centuries. What made the revolution particularly striking was how long these phenomena had been observed without being understood. Turbulence had been studied since Leonardo da Vinci sketched swirling water in the 15th century. Irregular variations in animal populations had puzzled ecologists since the field's inception. Poincaré had mathematically identified chaos in the three-body problem in 1890, but his work had remained a curiosity, too abstract and too troubling to integrate into mainstream science. Now suddenly, all these disparate observations snapped into focus. They were not separate mysteries requiring separate explanations. They were manifestations of chaos, a universal feature of nonlinear dynamics. The universe had been telling scientists about chaos for centuries. Only now were they learning to hear what it was saying. As chaos theory developed, scientists needed new tools to visualize and understand these strange systems. One mathematician would provide those tools by revealing a hidden dimension to reality itself. Benoit Mandelbrot was obsessed with edges, not the clean, sharp boundaries of Euclidean geometry that students learned in school, but the ragged, intricate, endlessly complicated borders that appear everywhere in nature. In 1967, he published a paper in the journal Science with a question so simple it seemed almost childish. How long is the coast of Britain? The answer, he demonstrated, depends entirely on how closely you look. Measure with a kilometer-long ruler and you get one answer. Use a meter-long ruler and the coastline gets longer because now you capture bays and inlets the kilometer ruler missed. Switch to a centimeter ruler and it grows longer still, wrapping around every pebble and rock. Keep zooming in and the length increases without limit, approaching infinity as your measuring tool approaches zero. The coastline paradox revealed something profound. Natural forms possess a kind of complexity that classical geometry could not describe. This was not merely a puzzle about measurement. Mandelbrot was identifying a fundamental property of nature that mathematics had overlooked for centuries. Mountains, clouds, trees, rivers, lightning bolts, blood vessels, galaxy clusters, all exhibited a peculiar kind of structure. They were rough at every scale. No matter how close you looked, you never reached a level of smoothness, never arrived at the simple shapes of traditional geometry. A cloud viewed from an airplane looked roughly similar to a cloud viewed from the ground, which looked roughly similar to a tiny wisp of cloud seen up close. This property, which Mandelbrot called self-similarity, meant that nature was repeating patterns within patterns, each level of magnification revealing new complexity that echoed the complexity above it. Mandelbrot had arrived at these ideas through a winding path that took him far outside the mainstream of mathematics. Born in Warsaw in 1924 to a Lithuanian Jewish family, he fled to France as a teenager when the Nazis invaded Poland. He survived the war years in rural France, his education disrupted, his family scattered. After the war, he studied at the École Polytechnique in Paris, but his mathematical style never fit the dominant French approach. Where French mathematicians prized abstraction and logical purity, Mandelbrot thought in pictures and patterns. He saw geometry everywhere, in economics, in linguistics, in the distribution of galaxies. His career took him to IBM's research center in Yorktown Heights, New York, where the company's tolerance for intellectual wandering gave him freedom to pursue questions no one else thought to ask. For years, Mandelbrot gathered examples of these rough, self-similar shapes. He studied cotton prices and found wild fluctuations that repeated at different timescales. He analyzed the flooding of the Nile and discovered patterns within patterns. He examined the distribution of word frequencies in language and saw the same strange regularities. Each field had its own vocabulary for these phenomena, but no one had recognized that they were all manifestations of the same underlying geometry. Classical mathematics divided the world into smooth curves and regular solids. into circles and spheres and straight lines, but the world Mandelbrot realized was made of something else entirely. In 1975, while exploring these ideas with early computer graphics, Mandelbrot examined a particular mathematical object that had been known since the early 20th century but never properly visualized. Take a simple equation involving complex numbers, z squared plus c, start with some initial value, plug it into the equation, take the result and plug it back in, repeat endlessly. For some starting values, the numbers spiral off to infinity. For others, they stay bounded, circling around in the complex plane forever. Mandelbrot asked the computer to color each point black if it stayed bounded, white if it escaped to infinity. What appeared on the screen stunned him. The boundary between black and white formed a shape of impossible intricacy. The main body resembled a warty circle with a smaller circle attached, but as you zoomed into the edge, new structures emerged. Spirals within spirals, tendrils branching into smaller tendrils, copies of the whole shape appearing in miniature along the boundary, each copy surrounded by its own ecosystem of swirls and filaments. You could zoom in forever and never reach the end of the detail. The equation was utterly simple, but it generated infinite complexity. Mandelbrot called it a fractal, from the Latin fractus, meaning broken or fractured. The Mandelbrot set, as it became known, was not just a mathematical curiosity. It was a glimpse into how simplicity creates complexity, how iteration produces infinite depth. The connection to chaos theory was immediate and profound. Chaotic systems, like the weather equations Lorenz had studied, also involved iteration, taking the output of one moment and feeding it back as the input for the next. The strange attractors that appeared in chaotic systems, those ghostly shapes traced out in phase space, turned out to be fractals. The Lorenz attractor, with its butterfly wing loops, had fractal dimension. If you zoomed into the surface where trajectories seemed to cross, you would find they never actually touched, but instead formed infinitely fine layers, a fractal structure hiding inside what looked like a simple surface. Chaos and fractals were two aspects of the same mathematical reality. Mandelbrot published his synthesis in 1977 in a book titled The Fractal Geometry of Nature. It was not a conventional mathematical text, filled with photographs and computer-generated images, written in prose that mixed rigorous mathematics with philosophical speculation. It argued that fractal geometry was the native language of nature. Coastlines, mountain ranges, blood vessels, turbulent flows, all were fractals. Traditional geometry, with its perfect circles and smooth surfaces, described the artificial world humans built. Fractals described the world itself. The philosophical implications were dizzying. For centuries, science had proceeded on the assumption that complexity must arise from complicated underlying causes. A complex phenomenon required a complex explanation. Fractals demolished this assumption. The Mandelbrot set emerged from an equation you could write in a single line. The intricate branching of a fern followed simple recursive rules. Complexity did not require complexity. It could emerge from simplicity through iteration and feedback. This raised a question that philosophy had never quite confronted. If a finite region of space could contain infinite detail, if a simple rule could generate endless variety, what did that mean for the structure of reality? Classical physics imagined the world as made of particles moving through space according to laws, each particle occupying a definite position at each moment, but fractals suggested that position itself might be more complicated than anyone thought. The boundary of the Mandelbrot set had infinite length contained in a finite area. The surface area of a fractal object could be infinite, even while its volume remained finite. These were not just mathematical abstractions. They described real objects, the surface area of your lungs, the length of your circulatory system, the complexity of a single snowflake. You could measure the coastline of Britain with increasing precision forever and never arrive at a final answer, because there was no final answer. The question itself assumed that length was a simple property, but for fractals, length depended on the scale of observation. The universe contained genuinely scale-dependent properties, features that changed as you changed your level of magnification. This was not uncertainty or ignorance. It was a fundamental property, of how nature organized itself. Mandelbrot gave scientists a new vocabulary for describing the world: fractal dimension. A number that could be a fraction measured how completely a fractal filled space. A smooth curve had dimension 1, a plane had dimension 2, but a coastline might have dimension 1.25, more than a line but less than a surface. This fractional dimension captured precisely the quality of roughness, the way the coastline was neither purely one-dimensional nor two-dimensional but something in between. Nature, it turned out, specialized in these in-between dimensions. The marriage of chaos and fractals transformed how scientists thought about complex systems. Weather patterns with their chaotic dynamics created fractal cloud structures. Turbulent flows generated fractal eddies within eddies. Economic fluctuations traced fractal patterns across time. The branching of lightning bolts, the distribution of earthquake magnitudes, the structure of galaxies, all displayed fractal characteristics. What had seemed like isolated oddities scattered across different fields revealed themselves as manifestations of deep mathematical principles. But perhaps the deepest revelation was about the relationship between simplicity and complexity, between the knowable and the unknowable. Fractals showed that you could understand the rule perfectly, know the equation with complete precision, and still confront infinite richness. The Mandelbrot set emerged from perfect determinism, yet exploring its boundary remained an endless task. Each zoom revealed new surprises, new structures, new patterns that no one had seen before. Determinism did not mean simplicity. Perfect knowledge of causes did not mean perfect knowledge of consequences. Fractals gave chaos theory a face, a way to see what had been invisible, but these mathematical discoveries were raising profound questions that went far beyond science. Laplace had imagined a vast intelligence that could know the position and velocity of every particle in the universe. Given complete information about the present, this demon could calculate everything that would ever happen, tracing forward through time with perfect accuracy. The future would be no more mysterious than the past, merely a mathematical consequence waiting to be computed. For more than a century, this vision had represented not just a thought experiment but an aspiration, a goal toward which science was steadily progressing. Every improvement in measurement, every refinement in calculation, every new equation seemed to bring humanity closer to Laplace's dream of total prediction. Edward Lorenz had destroyed that dream accidentally, but the destruction was absolute. The problem was not that his equations were too complicated, or that computers were too slow. The problem was written into the mathematics itself, into the fundamental relationship between present and future in any system displaying sensitive dependence on initial conditions. You could not predict the long-term behavior of such systems, no matter how good your measurements became, no matter how powerful your computers grew. The future remained hidden, not because of human limitations, but because of the nature of chaos itself. Consider what prediction actually requires. You must measure the present state of your system with some degree of accuracy. You must then use your equations to calculate forward in time. In a linear system, the kind that dominated classical physics, small errors in your initial measurement produce small errors in your prediction. If you know the starting position to within 1%, your prediction will remain accurate to within roughly 1%. Double your measurement precision, and you double your predictive accuracy. This is the mathematics that built bridges and guided spacecraft, the reassuring arithmetic of the clockwork universe. Chaotic systems betray this logic completely. In sensitive dependence, errors do not remain proportional to measurement precision. They grow exponentially, doubling and redoubling at a rate determined by what mathematicians call the Lyapunov exponent. If your measurement is wrong by 1 part in a million, chaos will amplify that microscopic error until it becomes as large as the system itself. The timescale for this amplification depends on the system, but the principle is absolute. Eventually, no matter how precisely you measured your starting point, your prediction becomes worthless. You might hope to escape this trap through perfect measurement, but the universe itself forbids such precision. Quantum mechanics places fundamental limits on how accurately you can know both the position and momentum of any particle. Heisenberg's uncertainty principle ensures that some imprecision is built into reality at its most basic level. Even if you could somehow circumvent quantum limits, practical barriers would remain insurmountable. To measure the atmosphere completely enough to predict weather weeks in advance would require knowing the position of every molecule, a task not just impractical but thermodynamically impossible. The act of measuring would add more energy to the system than the energy you were trying to measure. Weather forecasting became the paradigmatic case for understanding these horizons of predictability. Meteorologists had dreamed since the 19th century of calculating weather as Newton had calculated planetary motion. The equations governing atmospheric behavior were known, after all. The Navier-Stokes equations described fluid flow with elegant precision. If you knew the temperature, pressure, and wind velocity everywhere at a given moment, you should be able to calculate what would happen next. The arrival of computers in the mid-20th century made this dream seem tantalizingly close to reality. Lorenz's discovery revealed why that dream could never be realized beyond a certain horizon. Weather is chaotic. Tiny differences in initial conditions far smaller than any measurement could detect grow into completely different weather patterns within days or weeks. This was not a temporary limitation waiting for better instruments or faster computers. This was a fundamental property of the atmosphere itself. Meteorologists eventually determined that detailed weather prediction has a horizon of about 2 weeks. Beyond that point, the exponential growth of uncertainty makes specific forecasts meaningless. You cannot predict whether it will rain in London on a particular afternoon 3 weeks from now, not because meteorology is incomplete, but because the question itself has no determinate answer until the moment arrives. This realization forced a philosophical reckoning with concepts that had seemed clear for centuries. Determinism means that the future is fixed by the past according to natural laws. Given the complete state of the universe at one moment, the laws of physics determine everything that follows. Laplace's demon embodied this idea in its purest form. But Lorenz had shown that determinism does not imply predictability. A system can be completely deterministic, with every future state rigorously determined by present conditions and unchanging laws, while remaining unpredictable in practice. The distinction seems subtle, but it transforms everything. Classical physics had conflated determinism with predictability so thoroughly that they appeared to be the same thing. If the universe runs like clockwork, then surely we can read the time on the clock, calculate where the hands will point tomorrow, next year, next century. Chaos theory severed this connection. The universe might still be running according to deterministic laws, but those laws produce futures that cannot be computed, cannot be known, cannot be predicted no matter how much information we gather about the present. What humanity lost in this revelation was the hope of godlike knowledge. The Enlightenment had promised that reason and science would eventually illuminate everything. That mystery was merely ignorance waiting to be dispelled. The Victorian era, drunk on the success of Newtonian physics and thermodynamics, had believed that all the fundamental laws were known and only details remained. Chaos theory demonstrated that even with perfect laws and powerful mathematics, the future holds genuine unknowns. There are questions we can ask that have answers, but answers we can never calculate. Yet something was gained in this collapse of certainty. The acknowledgement of fundamental limits can be liberating. It frees us from the burden of impossible aspirations, from the frustration of failing at tasks that were never possible. Weather forecasters no longer beat themselves up for failing to predict conditions 2 months ahead. They have learned instead to provide probabilistic forecasts, to express degrees of confidence, to acknowledge uncertainty openly. This is not defeat but realism, not resignation but wisdom. The humility forced by chaos theory extends beyond meteorology, wherever sensitive dependence appears, and Lorenz had shown it appears almost everywhere. Prediction has horizons beyond which we cannot see. Economic forecasting, ecological modeling, climate projection, population dynamics, all these fields have discovered their own predictability horizons, their own versions of Lorenz's 2-week weather limit. The dream of controlling the future through calculation has given way to a more nuanced understanding. We can influence systems, nudge them, guide them probabilistically, but we cannot command them with certainty. There is something quietly profound in accepting that the universe contains genuine surprise, not randomness, not lawlessness, but deterministic laws that nevertheless produce futures that cannot be fully anticipated. The cosmos is neither the dead clockwork of Laplace's imagination nor the chaotic void of pure chance. It is something stranger and richer, a place where order and unpredictability intertwine, where simple rules generate infinite complexity, where knowing all the laws and measuring with impossible precision still leaves the future partly hidden. Lorenz had discovered this truth in a weather equation, but its implications rippled far beyond meteorology. If the future is unknowable even in principle, what does that mean for questions of free will, fate, and human agency that philosophers have debated for millennia? The question that had haunted philosophers for 2,000 years took on a new shape once Edward Lorenz demonstrated that determinism and predictability were not the same thing. If the universe follows inexorable laws yet remains unknowable in practice, what becomes of human freedom? The ancient debate about free will had always seemed to offer only stark choices. Either our actions are determined by prior causes, making freedom an illusion, or there is genuine randomness in the universe, making our choices arbitrary rather than free. Chaos theory suggested a third possibility, one that philosophers had never quite imagined. The classical problem was stated most clearly by the Stoics, though it troubled every philosophical tradition that took determinism seriously. If every event has a cause, and every cause itself has a prior cause stretching back to the beginning of time, then the future is merely the unfolding of what was already implicit in the past. When you choose coffee over tea this morning, that choice was the inevitable consequence of your brain state, which was the consequence of your experiences, which were the consequences of events stretching back before your birth. To believe otherwise seemed to require either denying causation itself or invoking some mysterious force that could act without being acted upon. Pierre-Simon Laplace had made this uncomfortably explicit. In a deterministic universe, a sufficiently powerful intelligence could predict every future event, including every human decision. If your choices can be predicted from prior conditions, in what sense are they really choices? The problem became more acute as neuroscience advanced. Every thought, every decision, every moment of deliberation corresponds to physical processes in the brain. Neurons fire according to the laws of chemistry and physics. No extra ingredient appears when consciousness emerges. If you could map the complete state of a brain, track every neuron and synapse and chemical messenger, determinism seems to demand that you could predict what that person would decide before they knew it themselves. Experiments in the late 20th century appeared to confirm this brain activity associated with a decision could be detected before the person reported consciously making the choice. Free will looked less like a philosophical puzzle and more like a persistent illusion, the feeling of authorship we attach to actions that were already determined by unconscious mechanisms. But Lorenz's equations offered something unexpected, a way for determinism to coexist with genuine unpredictability. The weather system he had modeled was completely deterministic. No randomness whatsoever appeared in his equations. Every future state was entirely determined by the present state according to fixed mathematical rules. Yet the system was unpredictable, not just hard to predict, but impossible to predict beyond a certain horizon, because measurement could never be perfect and tiny uncertainties grew exponentially. Perhaps human freedom occupied a similar space. Perhaps our actions are determined by the prior state of our brains and bodies and environment, following natural law without exception, yet simultaneously unpredictable, even in principle because the system is chaotic. This reframing dissolved some of the sting from determinism. The fear that troubled philosophers was not really that our actions have causes, but that we are puppets on strings, that some external intelligence could know what we will do before we do it, that our deliberations are theatre staged by unconscious mechanisms. Chaos theory suggested otherwise. Even if your brain is a deterministic physical system, if it is also a chaotic system, then what you will decide cannot be extracted from any measurement of your current state. not because of practical limitations or insufficient computing power, but because chaos places a fundamental limit on prediction. The future grows from the present according to law, but remains hidden even from the most perfect possible observer. Some philosophers found this liberating. If determinism without predictability is possible, then perhaps we can have our philosophical cake and eat it too. Our actions arise from our character, our values, our reasoning processes, all shaped by natural causes, yet remain genuinely open, not just to us, but to the universe itself. The feeling that you are deliberating, weighing options, choosing freely, would not be an illusion, but an accurate reflection of a process whose outcome is not written anywhere until it occurs. The future would be real, rather than merely unknown, created rather than discovered. Determinism would constrain without imprisoning, providing continuity and causal connection without predetermination. But this solution had limits that its proponents sometimes glossed over. Chaos is still determinism. The unpredictability is epistemological, not ontological. It concerns what can be known, not what is real. In a chaotic system, the future still follows necessarily from the present, even if we cannot calculate it. If you could somehow rewind the universe to an exact prior state, every atom in precisely the same position with precisely the same momentum, chaos theory does not suggest anything would unfold differently. The same initial conditions would produce the same trajectory through phase space, landing on the same strange attractor. Unpredictability is not the same as indeterminacy. Your brain state at this moment still determines, in the strict causal sense, what you will decide in the next moment. The fact that no one, not even you, can predict that decision in advance does not change the deterministic connection. This raised questions about what exactly we mean by freedom. Is unpredictability enough? If your actions flow necessarily from your brain state, does it matter that this necessity cannot be calculated? Some philosophers argued that what we really care about is not whether our actions are determined, but whether they are ours, whether they reflect our values and reasoning, rather than external compulsion. A chaotic brain would still be your brain, its decisions emerging from your character, even if shaped by prior causes. Others found this cold comfort. The feeling of deliberation, the sense that until you decide the matter is genuinely open, seems to require more than mere unpredictability. It seems to require that the decision is not already implicit in the present, that something genuinely new enters the world when you choose. The question took on new dimensions as researchers began to ask whether the brain actually is a chaotic system. Early evidence suggested it might be. Neural networks can exhibit sensitive dependence on initial conditions. The firing of one neuron influences its neighbors, which influence their neighbors, and small differences in timing can cascade into large differences in overall patterns. Some cognitive scientists proposed that chaos in neural dynamics might be functionally important, allowing the brain to be both stable and flexible, able to settle into patterns but also to shift rapidly between states. If thought itself is chaotic, then the unpredictability of chaos is not just a theoretical possibility but a physical fact about cognition. Yet this scientific question could not settle the philosophical one. Even if brain dynamics are chaotic, the relationship between chaos and freedom remains unclear. Chaos provides unpredictability, but freedom seems to require something more: agency. The sense that you are the author of your actions rather than their location. A chaotic brain is still a deterministic physical system, its trajectory through state space fixed by natural law, even if incalculable. The choices that emerge from that trajectory are your choices in the sense that they emerge from your particular brain, but does that constitute freedom in any robust sense? Perhaps the deepest contribution of chaos theory to the free will debate is not a solution but a reframing. The classical problem assumed that determinism and predictability went together, that a determined universe was one where everything could in principle be calculated. This made freedom seem to require either indeterminism, some fundamental randomness in nature, or a mysterious exemption from natural law, some way for mind to act without being part of the causal order. Chaos theory showed that this assumption was wrong. Determinism and unpredictability can coexist. This does not automatically vindicate free will, but it changes the landscape. It suggests that the real question is not whether our actions are caused, but what kinds of causes produce them, not whether they are determined, but by what they are determined. A decision that emerges from your values, your reasoning, your character might be free, even if determined, even if inevitable, given the complete state of your brain, because it is yours in the way that matters. The debate continues, as ancient questions tend to do when they touch on what we care about most deeply. Chaos theory has not ended the argument about free will any more than quantum mechanics did, but it has provided new concepts, new ways of thinking about the relationship between law and contingency, determination and openness. It has shown that determinism is stranger and subtler than the clockwork universe suggested, that even a world governed entirely by natural law contains more possibility, more genuine unpredictability than Laplace's demon could accommodate. Whether this unpredictability amounts to freedom remains an open question, but it is a different question than the one philosophers have traditionally asked, shaped by new understanding of what deterministic systems can actually do. Beyond metaphysics, chaos theory has changed how we think about cause and effect, about complexity and emergence, about what we can control and what we must accept. The Santa Fe Institute sits in the high desert of New Mexico, founded in 1984 by a group of scientists who recognized that something fundamental had shifted in how science understood reality. These researchers came from physics, biology, economics, computer science and mathematics, drawn together by a common conviction that the great challenges facing science were no longer problems of isolated systems, obeying simple laws, but questions about how complexity emerges from interaction, how order arises from apparent randomness, how the whole becomes something more than the sum of its parts. Chaos theory had opened a door, and beyond that door lay an entire landscape of phenomena that traditional reductionist science had never been equipped to explore. The Institute represented a quiet revolution in scientific thinking. For 3 centuries, science had achieved its greatest triumphs through reduction, break complex things into simpler components, understand the components, and you understand the whole. Newton reduced planetary motion to gravitational attraction between point masses. Darwin reduced biological diversity to variations acted upon by selection. Mendeleev reduced chemical variety to arrangements of fundamental elements. This approach had built the modern world. Yet chaos theory revealed its limitation. Even when you knew every component and every rule perfectly, the behavior of the system could still surprise you, could still generate patterns and structures that were nowhere present in the individual pieces. Complexity science emerged as the study of these emergent phenomena. A murmuration of starlings creates shapes in the sky that no individual bird intends or understands. An economy produces booms and crashes that no single transaction predicts. A brain generates consciousness through the interaction of neurons, none of which is itself conscious. The weather creates hurricanes according to simple physical laws, yet remains unpredictable beyond a few days. These are not exceptions or curiosities. They represent a fundamental feature of reality. Systems with many interacting parts can exhibit behaviors that are genuinely novel, that cannot be deduced, even in principle, from knowing the parts alone. The philosophical implications run deep. Reductionism had always carried with it a kind of promise that ultimately everything could be explained in terms of something simpler, that complexity was just simplicity wearing a disguise. If you could understand atoms, you could understand molecules. If you could understand molecules, you could understand cells. If you could understand cells, you could understand organisms. The chain of explanation would extend upward until everything found its foundation in fundamental physics. But chaos and complexity suggest that this dream, while beautiful, is incomplete. New principles emerge at different scales, principles that are real and consequential but that have no meaning at lower levels of organization. Consider an economy. You could, in theory, know the preferences and resources of every individual, the technology of every firm, the rules of every market. You could write down equations describing how people make decisions and how goods flow through networks of exchange. Yet from these components emerge phenomena like recessions, bubbles, and financial crises that cannot be predicted from individual behavior. The economy is chaotic in the technical sense, sensitive to initial conditions, bounded but non-periodic, deterministic yet unpredictable. But it is also something more. It exhibits what economists now call emergent properties, aggregate behaviors that arise from interaction but cannot be found in any single participant. The recognition that human systems might be fundamentally chaotic transformed how scholars thought about history, society, and politics. If small changes can cascade through complex systems in nonlinear ways, then historical contingency is not just an epistemic limitation, but an ontological fact. The course of history depends on details that might have easily been different. A decision made in haste, a message delayed by weather, a moment of courage or cowardice that shifts everything downstream. This does not mean history is random. Like the Lorenz attractor, it may follow deterministic rules while still being essentially unpredictable. The patterns matter even when the specifics cannot be foreseen. Social dynamics reveal the same signature. Fashions spread through populations in ways that resemble epidemic disease, but with feedback loops that make them chaotic. Political movements gather momentum or collapse according to mechanisms that are deterministic yet resistant to prediction. Cities grow in patterns that repeat across cultures and centuries, yet each city remains unique. The scholars studying these phenomena borrowed tools from chaos theory, phase space analysis, fractal geometry, sensitivity studies. They found that human systems, despite being composed of conscious agents with intentions and beliefs, often behaved like other complex, chaotic systems in nature. This realization brought both humility and insight. Economics had long aspired to the predictive precision of physics, building elaborate models that promised to forecast markets and manage growth. But if economies are chaotic systems, such precision may be impossible in principle, not merely difficult in practice. The question then becomes not how to predict perfectly, but how to build resilient systems that can adapt to surprises, how to recognize the early signs of instability, how to work with uncertainty rather than pretending it can be eliminated. The same lesson applies to ecology, to climate, to any system where many components interact in non-linear ways. Traditional management approaches assumed that if you understood the parts and controlled the inputs, you could determine the outcomes. Chaos theory suggests a different stance. Acknowledge that control is limited, that surprise is inevitable, that the goal should be adaptive resilience rather than brittle optimization. This represents a shift not just in technique but in philosophy, from mastery to partnership, from control to participation. Yet accepting unpredictability does not mean embracing nihilism or giving up on understanding. Chaotic systems have structure. They have attractors, regions of phase space that the system tends to inhabit. They have patterns that recur across scales. They have sensitivities that can be mapped even when specifics cannot be predicted. The weather may be unpredictable beyond 2 weeks, but we understand why summers are warmer than winters, why hurricanes form in certain regions, why jet streams meander. We cannot predict which specific snowflake will trigger an avalanche, but we can understand the conditions that make slopes unstable. Knowledge remains possible and valuable even when perfect prediction is not. There is wisdom in this acceptance of limits. The dream of total prediction carried with it a kind of existential burden. If everything could be foreseen, then nothing genuinely new could ever happen. The universe would be merely playing out a script written at its beginning. Chaos theory reveals that even in a deterministic universe, genuine novelty emerges. The future is not merely unknown, but unknowable, not because we lack information, but because the nature of chaotic systems makes perfect prediction impossible. This unpredictability may be what allows for creativity, adaptation, and meaningful choice within a lawful cosmos. The strange beauty of chaos lies in how it interweaves order and disorder. The Lorenz attractor never repeats exactly, yet it traces a recognizable shape. Fractals are infinitely detailed, yet governed by simple rules. Chaotic systems are deterministic, yet produce behavior that appears random. This dual nature suggests that the old dichotomy between order and chaos was false. Reality is neither perfectly regular nor purely random, but something richer, organized complexity that cannot be compressed into simple formulas, patterns that emerge and dissolve, stability that exists within perpetual change. Standing in that place between knowing and not knowing, between pattern and unpredictability, may be the most honest relationship we can have with a universe that is far stranger than either the clockwork cosmos of Laplace or the random chaos that some feared chaos theory revealed. The world follows laws but surprises us. Systems have structure but resist control. The future unfolds from the present yet remains genuinely open. This final chapter synthesizes the journey from Laplace's demon to Lorenz's attractor, from the dream of perfect knowledge to the wisdom of acknowledging mystery.